Hello, everyone. In this video, our team is going to demonstrate our project, Secure IoT. I am Biao, and my teammates are Manoj and Sachin. In today's modern living, our home and workplace are equipped with smart appliances thanks to the emerging Internet of Things technology. We have smart light bulbs, security cameras, remote controlled doors and doorbells, cleaning bots, and smart thermostats, etc., all connected to our internet router. Though nowadays, our router and personal devices, like computer and phones, have better security measures on them, it is not the case for these Internet of Things technologies. They are designed to be lightweighted, and as a result of that, they are very vulnerable to malicious attacks. Imagine a scenario that a hacker is trying to hack into a smart light bulb in your home and hijack it, then sending malicious packets to your home router, and thereby hijacking all the other devices connected to your router, gaining access to all of your IoT devices and your computers and phones. You might be thinking, what's the harm in that? The worst the hacker can do is to turn my lights on and off as a prank and look at the cat pictures in my phone. But little do you know, there have been a number of recorded IoT attack incidents that lead to financial losses and life-threatening security concerns. We have a smart fish tank hacked in a casino, leaking 10 gigabytes of data. We have a building central heating system in Finland hacked, leaving the residents cold in the Scandinavian winter. On the more serious side, several hackers demonstrated how they can hack smart light bulbs to bot conversations in office meetings, hack pacemakers to shock patients, and hack the controller of a Jeep car, gaining full control of the vehicle's steering wheels. A security solution for IoT is urgently needed. There are currently 18 billion IoT devices used by corporations, government operations, homes, and the number of IoT will only increase more and more as the 5G technology emerges in the following years. The IoT market has a projected annual growth of 16.7% for the following 5 years, sitting currently at 300 billion USD and targeted to rise to 650 billion US dollars in year 2026. Just in the first 6 months of 2021 alone, there have been 1.5 billion documented IoT-related attacks, and the number doubles every 6 months. The existing software security solutions include firewalls, encryption, access control, network surveillance, and there are a lot of named companies in this business. However, these software solutions are too slow to catch up with the growing throughput in today's internet, and they're only going to draw back further as 5G speeds up internet traffic in the foreseeable future. To explain how our solution is better, allow me to walk through an analogy with you. Imagine that you're traveling on plane and have to go through all the security measures to get to the plane. The traditional security solution is just like how we go through airport security. We need to first go to a kiosk to print out our tickets, wait in the line to check in our baggages, and then go through another line to verify our documents, then go through yet another line to get ourselves inspected before finally walking to the gate. The process is very linear and time-consuming. In our approach, we parallelize the process to save time. Imagine that while you're printing your tickets, a staff member comes by and collects your check-in bags and checks them in for you. Another staff member verifies your documents, while you yourself is being inspected. Within minutes, all three processes are done and you're walking to your gate. And in the situation where a security concern is raised, let's say if your passport is fake, then airport security can also find out within minutes and transfer you to the police fast. Next, my teammate Manoj is going to explain the technical details of our hardware solution.
For the purpose of IoT security, we define a corrupted node as a node that is either not behaving properly or trying to send a malicious packet to another node. Since these IoT devices are relatively simple, their behaviors can be easily quantified. One such behavior could be accessing nodes they're not supposed to. Why would, say, your thermostat want to talk to your outdoor sprinkler? Or why would your AC remote ask your air conditioner to switch to 45 degrees Celsius when the air conditioner is only capable of doing 15 to 30 degrees Celsius? So to implement this, we have a data filter and two CPU cores, both of which are working on a RISC-V instruction set with an added special interrupt. The data comes into a buffer and that stores it till it is processed. Once the data is in, we load the header into core 1. Inside core 1, we have four threads running simultaneously. So the first thread is going to see if the source is a valid source, that is, if it is in your network. Why would your neighbor's light bulb want to talk to you? Your thermostat, that doesn't make sense. So here we see the thermostat is a valid source. While this is happening, thread 2 is looking for a path. There are other behaviors that can be programmed in the remaining threads, but for the experimentation purposes, we are only choosing to implement the behavior of this behavior. As we can see, thermostat cannot talk to the sprinkler. So we generate a special interrupt and then send it to core 2. Now let's say that the path is valid. So the packet passes through core 1 and goes to data filter, but the data has malicious packets. So in this case, we have a data filter. The data filter has 4 pattern matches, which looks for 4 different malicious patterns simultaneously. As soon as the data comes in, we take the source ID from the data, and then the pattern matches are going to look for the pattern in the data itself. If a pattern is found, we are going to create a same interrupt created by core 1 and then send it out to core 2. When the core 2 gets an interrupt from either core 1 or the data packet, it also has one thread that is going to take this source and it is going to add it to an invalidated list. This list is shared between core 1 and core 2. However, core 2 is the only one allowed to write into it. Core 1 can read from the updated list and drop the packet simultaneously. As you have noticed, there are other threads available in core 1 and core 2. These can be programmed to look for different behaviors. Now let us look at the demonstration of this hardware.
Here we see the terminals for the net FPGA, node 0, node 2 and node 3. Let us start by programming our net FPGA. This script does CPCI reconfiguration and reprogramming, and then followed by bit file loading, followed by RKDemon initialization. Later we also program the cores present inside our design through the interface designed. According to the experiment setup, node 0 can talk to any of the other nodes. Let us test this notion out by pinging other nodes from node 0. We can see that node 0 can ping node 1, node 2, and node 3. As per the experimental setup, node 0 can ping node 3, but node 3 cannot try to talk to node 1, node 0. But node 3 can only talk to node 1. Let us test this notion. Let us test this notion out by pinging from node 3 to node 1. Now let us ping node 0 and see what happens. As we can see, all the packets are being dropped by the router, hence we don't see any reply from node 0. The router has also blacklisted node 3. We can test that by trying to ping from node 0 to node 3 now. We know that there is a link between node 0 and node 3 because we were able to ping it previously. Let us see what happens if we try to ping node 3 now. As you can see, all these packets are also being dropped because node 3 is now blacklisted by the router, and all the packets going from and to node 3 are being dropped. Now we know that node 0 and node 2 are healthy. Let's just do a iperf throughput test for node 0 and node 2. A simple iperf test shows that we have around 942 megabits per second. Now let us try and send a good packet of around 1 GB data and see what happens. The good packet doesn't contain any malicious data. As we can see, the throughput is around 942 megabits per second. Now let's see what happens if we try to send a bad packet, that is a data pattern containing a malicious data. Since this is a TCP communication and all the packets are being dropped by the router, we don't see any acknowledgement from either nodes. Therefore, they're always waiting to listen from each other. So I'll be stopping this manually. However, the router has now invalidated to node 2 and has blacklisted it. Now we'll test that out by pinging node 2 from node 0 after we end the throughput test. We have stopped the throughput test now, and then I'm trying to ping node 2. All the packets to node 2 are being dropped because node 2 has been blacklisted by the router. Now let us ping node 1 and see, because we know that node 2 and node 3 have been invalidated, but node 0 and node 1 are the only valid nodes present. As we can see, node 1 is still alive and we are able to communicate with it. Now let us reprogram the router. This will bring back the node 0, node 2 and node 3. We can adjust this by initially blacklisting node 2 and node 3 while we are invalidating them, while we are restarting the router itself. But for this proof of concept, we are not doing that. As we can see, node 2 is back, node 3 is back online. So is node 2. From this test, we can also see that we get a throughput of around 942 megabits per second with the router.
To benchmark this, we use Snort, an open source packet sniffer tool. Snort has two modes of operation: intrusion detection, in which it looks at packets and sends alerts when it finds malicious content, and intrusion prevention, where it actively drops the packets that are malicious content. It has a hyperscan mechanism which does a fast pattern matching on the data it receives. The Snort sits between the sender and the receiver and looks at the data and drops them as it is. We calculate the overall throughput of this system as well. A lot of research has been put into looking at Snort's performance. One author published a thesis on Snort's performance earlier this year. As you can see, Snort can achieve 626 megabits per second at a cost of packet dropping. As illustrated here, it achieves this by doing about 1.6% packet dropping. This could be dangerous as those dropped packets could be malicious. So for the 0% packet drop, Snort can perform at 254 megabits per second. The author for this also claimed a 20% CPU utilization. Various other researchers have studied SNOT and the CPU, and the CPU utilization numbers range from 10 to 20%. As illustrated here, our solution can perform at 942 megabits per second, while SNOT can perform at 254 megabits per second. It is evident that our implementation is 3.8 times better than SNOT implementation performance-wise. A typical CPU these days consumes 45 to 65 watts of power. Extrapolating the lower side on this and to the 10% lower side of 10 to 25% CPU utilization claimed by the various researchers, we arrive at a power consumption of 4.5 watts per SNOT. We calculated the power consumed by our design using XBAR, and as illustrated here, it is about 450 milliwatts. This illustrates that our implementation consumes an order of magnitude less power than SNOT.
We also compared our estimate results to the most popular home use router on the market to see if they're power efficient enough for these routers. The data is from an appliance power usage database, and we picked the most popular models listed. Keep in mind that some of the lower power consuming models are discontinued by their manufacturers, and that's why we're excluded them from our chart. The light green represents the minimum average operating power, and the darker green represents the maximum average operating power, while the red is our module's power cost. From the chart, it is clear that our design is power efficient enough to be added to today's most popular routers. There are some future work that can be done for our project. Initially, we plan to incorporate a self-healing mechanism to further ensure the safety of our system, as shown on the slides right now. Supposedly, we have 3 network nodes in our network, node A, B, and C. And node B is trying to send a packet. While node A is inspecting the packet, it finds out that node B is likely a corrupted node. So now what node A is going to do is to tell all the other nodes in the network that B is corrupted. So all the nodes that have a connection with B will cut off their connection with B. And node B itself will start a self-healing process to check what is going on. Meanwhile, node A and C will establish a connection between themselves to ensure the network is working and that node B is isolated from the network.
Now I will be explaining the algorithm for updating the route. In our system where we have multiple nodes in the topology, we detect the node connection issue, the corrupted packet node, through a hardware filter. The node connection issue is detected here, and the hardware raises an interrupt to the software through the interrupt service routine. In the interrupt service routine, we set a reroute flag, and this particular reroute flag is read by a software polling software, which based on setting of the reroute flag runs the rerouting algorithm. To explain this in detail, we have these many blocks in our systems, which involves hardware filter, which passes a special packet, and we have a software interrupt service routine. We have a polling software, and along with a routing table, which contains the network topology. Clearly, we can see that this hardware filter detects the malware packet and then sends a special packet to the software. This particular special packet, along with that, this hardware filter raises an interrupt which invokes a software interrupt service routine, which takes in the packet, passes it, and stores the data. This also sends a route flag to the polling software, and this polling software fetches the particular data which is taken from the past packet and then processes it. This processing involves IP address mapping and update of IP addresses to the routing table, and then detecting the node number and then generating the IP address and other additional network based information. And then this process data is sent to the routing table, where we have a routing table update algorithm, and then based on the output of the routing table algorithm, the routing table is updated.
So as explained in the presentation, we have a polling function running in each node. So every node is polling for a corrupted packet from every other node, and based on the special packet sent by the hardware, it gets updated. The routing table needs to get updated. So let's see, like we'll try to send a corrupt packet from one of the nodes. So you can see that this routing table got updated accordingly. Like it passed that node, but node number 3 is at fault, and then we can see that basically the IP routing table got updated from 3.3 to 0.3 here. So let's try to see send one more corrupt packet from another node. So here we can see that the routing table got updated accordingly from this to this, where the network gets removes that particular node from the network and tries to reroute and updates its IP address, which is getting connected to the other member. So clearly we can see that the network updates accordingly, and the network is safe from the internet hazards.
However, due to timing constraints, we could not incorporate this part of the design to our project on Teacher Lab.
We began this project by looking at various serious problems that networks today face. Upon finding about the serious threats due to insecure IoT networks, we began researching existing solutions. Later, we began formulating ideas regarding a custom security solution. After that, we began implementing an ideas followed by a RISC-V instruction-based course. Then we modified the core and integrated them with the intrusion detection system. Later, we used NOT and software-based node dropping mechanism on an experiment created on Data Lab to get the results. Throughout the process, we have learned about the entire life cycle of a product from conception to production. We'd like to use this opportunity to thank our professor, Professor Yang Cho, for providing the guidance that helped us finish this project. Thank you.